Thank you, Justin, for that lovely introduction. As he said, I'm Elinor Gates, and I'm an astronomer at the Lick Observatory. So let me see a show of hands. Have any of you actually been to Lick Observatory east of San Jose? Oh, a couple of you. That's great. It's not real close, but it's not so far away. You've probably seen it. It is sitting on the hills east of San Jose. There are a bunch of white domes up there. And it's an astronomical observatory, which means each one of those little domes, each one of those domes has a telescope in it. And as an astronomer's job is to study the universe and all the things in it and try and understand how things work, how they change with time, how they formed, what the history of the universe was, etc. So it's a big place. There are lots of things we don't know. One of my jobs at Lick Observatory is to work on the instrumentation, make sure that the telescopes work as well as possible, so that visiting astronomers to the observatory and all the astronomers that use the facility can get the data they need for whatever they are studying, be it planets in our solar system or, like me, these supermassive black holes at the centers of distant galaxies. Before I talk about my research and telescopes, I'll give you a little bit of my background. I went to the public school system. I grew up in Connecticut, so I went to Amity High School, and I was a science nerd even back then. I took all the science classes, chemistry, physics, AP physics, because I really liked physics, math, and calculus. And I went on to college. Whoops, I skipped a slide here. Sorry, this is being... So I knew I wanted to do math in college because I really loved math, but I also wanted to use it for something. And I wasn't sure what science I wanted to do, so when I went to college, I chose a college, Mount Holyoke College in Massachusetts, that had really strong science programs. And my freshman year, I was taking geology and physics and astronomy, trying to figure out what I wanted to do. But black holes and the weirdness of them and the strange math or physics that happens around them really interested me. So I ended up doing a double major in math and astrophysics. And believe it or not, I never looked through a telescope until I was already an astronomy major. And I looked through the 8-inch Clark refractor at Mount Holyoke College, and that really excited me because I was able to see one of Jupiter's moons transit in front of Jupiter and see that things were moving in real time, and I could see, astronomy was even more dynamic than I thought it was in sighting. I then went on as an undergraduate to take advantage of research opportunities. I worked for the International Astronomical Union Minor Planet Center, taking data from all over the world on asteroids and trying to figure out their orbits and if they were new asteroids or not, and they honored me with naming an asteroid after me for that work. And then I also worked at the National Radio Astronomy Observatory studying quasars, these massive black holes at the centers of distant galaxies that are sucking in tons and tons of material. And that material, before it disappears into the black hole, becomes incredibly hot and bright. And some of it appears to move faster than the speed of light when you look at it in radio wavelengths. And so, it's an optical illusion. It's not really going faster than the speed of light, but I got to study things like that. And I was just hooked. I need to go to grad school for this. So I went to the University of New Mexico, and grad school takes a while. I got my master's and my PhD in physics with an astrophysics concentration. And while I was there, I was studying how to measure the distances to these elliptical galaxies out there in an accurate way. The elliptical galaxies are tough. They're sort of like big, ellipsoids, sort of football-shaped things, or egg-shaped things, I should say. Balls of stars, huge, billions and billions of stars. But because they're featureless, it makes them a little tougher to measure the distances to than other types of galaxies. And I also started working on education programs. I worked for the Lodestar Project, where we were taking portable planetariums and telescopes out to rural areas of New Mexico, as well as building a planetarium and telescope to add to the New Mexico Museum of Natural History in Albuquerque. I also worked for the Air Force while in grad school, working on new technology called adaptive optics. And one of the telescopes there, I worked with, one of the telescopes I worked with there with a big laser talk about lasers too this talk. This new technology we're using in the military, not for astronomy. They were looking at satellites, but it's way cooler to use this technology to improve your views through telescopes and get better data. So what do I do at Lick Observatory? Well, mostly I use our biggest telescope. This telescope in the picture here is the Shane 3-meter telescope, which means the primary mirror that collects the light is 3 meters or 10 feet in diameter. It's huge. The telescope is about 60 feet long. And there are two advantages to having a big telescope. One is you collect more light, so you can look at fainter objects and observe more of the universe, either because it's intrinsically faint and nearby, or really faint because it's super far away. The other advantage, in principle, of a big telescope is the bigger diameter of your telescope, the smaller details you can see. Now that's great, you want to see all the details. Unfortunately, there's this confounding thing called the Earth's atmosphere that makes life difficult. And how many of you have ever looked up at the night sky and seen the twinkling stars? Yeah, that's virtually everybody. Absolutely beautiful, lovely, so pretty, romantic, but terrible for astronomy and doing science. Because you have the star, and we have the turbulence of the Earth's atmosphere represented by these little red lines, and then you have your telescope, and that turbulence blurs your image. And so it turns out that no matter how big your telescope is, it won't really see details any better than maybe an 8 or 10-inch telescope in your own backyard, because the Earth's atmosphere blurs things. Now, there are a couple ways we could get around this, but first, hello. There we go. This is sort of the effect of it. Ideally, your object is a nice, perfect little point. The Earth's atmosphere is constantly moving and changing, so if you take a super short exposure, like a few milliseconds long, your star actually looks like a lot of little speckles, a speckle image. And if you take a really long exposure, all the speckles blur together and you give you a big blob. So that's non-ideal. Ideally, you want everything to look like that image on the right. Everything's all nice and perfect. So there are three ways. Hello. 3 ways we can get rid of this effect. One, don't look through the Earth's atmosphere. Go up into space. That's great. We have the Hubble Space Telescope, the James Webb Space Telescope. These give you super beautiful views of the universe. But there are very few space telescopes. And there are lots and lots of astronomers and lots of science. So you have to compete with every other astronomer in the world. So we need to make best use of our ground-based telescopes. There's another technique called speckle interferometry, and that's where you, on the previous slide, you saw all those little speckles. You can, in computer software, actually take all those speckles, stack them on top of each other, and create a high-resolution image, but it only works for super bright targets, so it's really limiting. But we developed this technology called adaptive optics that allows us to, in real time, measure the turbulence in the Earth's atmosphere. We look at a bright star. We know the bright star should be just a pinpoint. We can measure like up to 1,500 times a second with my system. There are systems that can do it faster, but the system I use most, 1,500 times a second. See what the instantaneous blurring is, and then we can put anti-turbulence on a little mirror, small mirror, to correct for it and give us nice sharp images through the telescope. And this is great. The problem is you need a bright star, or you need to be pretty close to a bright star, because if you move too far away, you won't be measuring the same turbulence. This is remarkably effective, and I have this little video or animation from the Gemini telescope that'll show sort of intuitively what we're doing with adaptive optics. You can see light comes through the telescope, hits the primary mirror, goes up to the secondary mirror, comes through a hole in the primary mirror, back to the instrument. The Gemini telescope has a number of instruments. You can pick and choose which one to use at any time. We're going to choose the adaptive optics system. We have light coming through. We have our deformable mirror here. We have a beam splitter, so blue light's going to our wavefront sensor. That's the gizmo that's measuring the turbulence. And then the longer wavelength light, the infrared light is, or the red light in this case, is going to our science camera. So you can see these little potato chips flying through the system. These are sort of our aberrated images blurry images, so that's the turbulence sort of going through the system. Now we turn on our wavefront sensor. Now it's going to send anti-turbulent signals to the deformal mirror. Now the deformal mirror, this is hugely exaggerated. You can't see it move with your eye. But you can see that the turbulence gets corrected, and then it takes all that light and focuses it on the camera, and instead of this blurry blob, we should get a nice point-like image. So I hope this gives you an intuitive idea of what is going on with adaptive optics. Of course, that makes it look all super simple and intuitive. Of course, in reality, it's not. It's a huge engineering problem and computer problem. This technique was originally thought of in 1958 by Horace Babcock, an astronomer, but it wasn't until the 1980s and 1990s that the technology caught up, allowing us to start using this technology. And now, of course, we're constantly upgrading it because technology continues to advance. Computers get faster, we have better components. But this is what an actual adaptive optics system looks like. We've got our science camera here, we've got the wavefront sensor there that measures the turbulence. We've got 2 deformable mirrors actually in our system at Lick Observatory. We have one woofer that does the big corrections like image stabilization, focus astigmatism, coma, the big distortions, and then we've got the tweeter that has a lot more actuators, which are the little pistons or ways of changing the shape of the mirror. That does all the high frequency corrections to sort of the next level. It works amazingly well. And it took many years to develop this technology and build this system. Deformable mirrors look kind of boring. This deformable mirror is our woofer, has a silver coating, only 52 actuators to change its shape, but it can move bigger amounts. And then we have the MEMS device. You'll notice it's gold coated. Since we're doing science in the near infrared, the gold coatings are actually super reflective in the near infrared, the light redder than our eyes can see. But this has 1,000 actuators, so it can really do complicated shapes to correct for the atmospheric turbulence. And this is how it works. So this loop is showing you sort of some very quick data showing without adaptive optics, you can see how much the star is bouncing around. The top row is the star New Ursa Majoris. It's just a single star. And then we have Hipparcos 59366 in the bottom row, which is actually a binary star. You can see without adaptive optics, it's hard to tell if it's one or two, either one of those is 1 or 2 stars. With just the tip tilt correction, that's the image stabilization, just making sure things are staying centered. You can start seeing that the top one is a single star and the bottom one's a binary. But when we have the full adaptive optics running, you can see very clearly it's 2 stars. We have all the resolution, we're getting the most out of the telescope we can. So we use this for all sorts of interesting science. If this moves forward, come on. So one of the things we study at Lick Observatory are the planets in our own solar system. There's a lot we don't know about them. So this is Uranus. Unfortunately, it's a little blown out here, but without adaptive optics, this would just be one big blob. With adaptive optics, unfortunately, you can't see it on the screen here, but there are actually storms on the surface of Uranus, and we can track them over time. It also has a faint ring. I don't know, I hope you can see it there. So Uranus has a ring surrounding it, just much like Saturn has a ring around it. But we can study those storms, and in fact, we were so successful with implementing this technology at Lick Observatory that we then implemented it at Keck Observatory. So this is Neptune, which is Keck Observatory is a 10-meter diameter telescope, so it's more than 3 times the size of our biggest telescope at Lick Observatory. That's Neptune. Can't see a lot of features. When you use adaptive optics, you could suddenly see cloud bands, storms, and Neptune has a ring as well. And so I've been working with a crew at UC Berkeley to study the storms on Neptune and track them over years. And you need a lot of time to do this, so between Keck and Lick Observatory, we tracked the drift rates of the storm. How fast are they going around Neptune? What are the wind speeds at the upper levels of Neptune's atmosphere? So we were able to figure that out. We also saw that, wow, the storm sort of went away in 2020. And now they've come back. It turns out the number of storms on the surface of Neptune is correlated with the solar activity. Our sun goes through a solar cycle every 11 years, where it has very few sunspots, and then over the next 5-6 years, it gets lots and lots of sunspots. We happen to be at that high sunspot number right now in 2025, and then they'll decrease again. And it's just a cycle, and it turns out the number of storms we see on Neptune is correlated with the solar activity. So the sun has a lot of effect on Neptune's weather. The problem is that to measure the atmospheric turbulence, you need a bright star. And that's great. There are lots of bright stars, so you need to be really close to a bright star. It turns out only 1% of the sky is near enough a bright star for this technique to work. And astronomers are like, well, that 1% of the sky is really interesting, but none of the objects I study have a bright star near that by them. So we need to be clever and figure out a way to use this technique when there is no bright star. So we use a laser to create a star wherever we want one. Lick Observatory pioneered this for astronomy, and in fact that's part of how I got my job there, is they needed someone to work on this technology and make it work so that astronomers could really use the system. So what we do is we take a yellow laser, it's tuned to a certain color of light that sodium atoms in our atmosphere really like, and it turns out 60 miles or 90 kilometers over our heads in the mesosphere is where meteors burn up. When a meteor hits the Earth's atmosphere, that's when the atmosphere gets dense enough, it burns up. And meteors are made of all sorts of things like nickel, iron, potassium, calcium, sodium. And so every time there's a meteor shower, like the Perseid meteor showers in August or the Leonid meteor showers in November, you get a new supply of sodium. It eventually reacts with other things, percolates out, but every year we get a new supply. But we use a laser tuned to the special color yellow-orange, and that causes those sodium atoms to fluoresce so that we can make a laser wherever we need one to measure the turbulence. And so it's great technology. It's hard, but it works. But it's a powerful laser. The little laser I'm using to illuminate things on the screen is probably 0.5 to 5 milliwatts, somewhere in there, mostly safe, not entirely safe. The laser we're shooting out the dome is like 10 watts of laser power, thousands of times more powerful than the little laser in my hand. Now that has some hazards that we have to worry about. Things like there are airplanes up there, and we don't want to hit an airplane. Now, if we hit an airplane, it's not going to explode. It's not going to be flaming debris coming around the observatory. But we could blind the pilot. And if they're coming into land at San Jose or San Francisco or Oakland or any number of other airports, it would be really, really bad if your pilot was blind. So we have plane spotters outside. So you can see one of our plane spotters got up and walked around during this long time exposure with their red kill button. So they're looking around for airplanes coming towards the laser. If they see a airplane coming, they can tell our laser operator an airplane's coming and they need to shut down the laser. Or if it's coming too fast or communication fails, they just push the red button, laser turns off, everyone's safe. As a backup system, we actually have a radar system mounted on the top of the telescope to be absolutely sure we do not hit an airplane. But it's a regulatory nightmare with the FAA, and I have to fill in a lot of paperwork. One of the not so fun jobs of being an astronomer at Lick Observatory. The other thing is that a lot of the light we send up with our laser actually never hits a sodium atom in the atmosphere, goes right out into space. Turns out our laser is powerful enough. It's a danger to astronauts on the space station or any of the satellites with downward-looking cameras like weather satellites or spy satellites. So I get to work with Space Force Space Command to make sure that we don't illuminate anything in space we shouldn't. And so I have to send off a list of targets we want to look at with our telescope with the laser, and they send me back a list of you need to shut down at this time and this time and this time to make sure we don't hit any satellites. Again, regulatory hassle, not the most fun part of their job, except that I have Space Command's phone number on my iPhone, which is awesome. So anyway, what can we do with the laser? Well, it works just like Natural Guide Star adaptive optics. And here's a little tiny object that without adaptive optics just looks like a blob. With adaptive optics, you can see there's a bright point in the center and this ring. It turns out this is what we call a planetary nebula. So our sun, when it dies in roughly 5 billion years, it's not coming too soon, will look like this, that the star, when it dies, sort of huffs off its outer layers, creating that donut of gas, and the core collapses into a white dwarf star. And so we can study this object with great detail in ways we couldn't without the adaptive optics technology. Another exciting discovery with this technology that wasn't available before was looking at the center of our galaxy. Center of our galaxy, without adaptive optics, things are kind of blurry. You can't tell how many stars there are. With adaptive optics, you can see the stars. And it turns out, at the center of our galaxy, there's a black hole. And some of those stars are orbiting the black hole. And it turns out that the laser helped us a lot in making these sorts of measurements. That using a natural star, I've forgotten which star off the edge of the field they were using for measuring the turbulence. But they wanted to look right at the center where that little plus is. And with the laser, we could point the laser right at the center of the field, measure the exact right turbulence, not turbulence that's similar but a little off, and got better images. And over 20 years, they were able to measure the orbits of various stars around the center of our galaxy. And Andrea Ghez led this project. And she measured the mass of this black hole at the center of our galaxy to be 4 million times the mass of our sun. So it's a pretty big black hole. And this work was awarded the Nobel Prize in the year 2020. So it's very satisfying to me to help work on technology and techniques for doing astronomy that have led to a Nobel Prize. I'm sure there are going to be more Nobel Prizes that utilize this technology. Now, some of my own research, not quite as pretty pictures. As I said, I study quasars, these supermassive black holes at the centers of distant galaxies. And because there's stuff falling into these black holes that gets very hot, emits enormous amounts of light, that core of the galaxy can be brighter than the whole rest of the galaxy combined. And if it's far away, like this one in this image, all you see is the core. So what I did is I used adaptive optics so I could shrink that core down to something small, and then I've actually subtracted it here so I could actually see the galaxy around the quasar and figure out, is that galaxy a spiral galaxy? Is it an elliptical galaxy? Does it have other companion galaxies? It does. This is a little galaxy cluster. There are 2 other galaxies there. But there's a correlation between the mass of the galaxy, and now that I can see the galaxy, I can make an estimate of its mass, and the mass of the black hole of its core. And so the mass of this black hole in this galaxy, we figured out, is somewhere between 340 million and 1.3 billion times the mass of our sun. So this is a much bigger black hole than what sits at the center of our own galaxy that Andrea Ghez figured out. There are other ways to use this technology, and so we have a plan to use it for one of our telescopes at Lick Observatory called the Automated Planet Finder. So this is a telescope that is discovering new planets around other stars. It does it in a different way than the previous speaker, Tom, talked about. He was directly imaging planets around other stars. We're not directly imaging them here, but the technology Tom was using for his planet discoveries is adaptive optics. It's the sort of thing that I've been working on and helping develop for other telescopes. But here, if you have a planet orbiting a star, the gravitational tug of that planet causes the star to wobble back and forth. And you can see it greatly exaggerated in the animation. But we can measure that wobble. And with our Automated Planet Finder telescope, it can measure the wobble to an accuracy of 1 meter per second. So I'm just moving, probably not even as fast as 1 meter per second. I mean, it's not a fast speed. So it's amazing that we can make measurements that accurate. And in fact, we've discovered many planets around the stars. So this is sort of a graphic just showing how we're using the Doppler effect to allow us to measure the wobble of the star. And the Doppler effect, you've all heard it if you ever have a siren of an ambulance coming towards you and then away from you. You notice the pitch gets higher as it's moving towards you, gets lower as it's moving away. The same thing happens to light. When something's moving towards you, the light gets shifted to the blue. When it's moving away from you, it gets shifted to the red. And so we can measure that small shift in red and white and infer the presence of a planet. We're not seeing the planet directly, but not only can you discover one planet, like in 70 Virgo, in this plot here, but you could discover multiple planets. So we've discovered other solar systems out there in the universe with this particular solar system around HD 219134. Not a very exciting name, we know, but there are 6 planets in that system. So, but how do we make our telescope work better so we can discover more planets or discover them faster? And that's where adaptive optics comes in. Right now, to make these measurements of how fast that star is wobbling back and forth, you need to send the light down through a little narrow slit. The Earth's atmosphere turbulence means that a lot of that light misses the slit. It ends up off to one side or the other. And so we can use adaptive optics to make sure that more light makes it down the slit and things are more stable. And for the Automated Planet Telescope, we're planning to use sort of a new technology of adaptive secondary mirror. So we won't be adding any new mirrors to the instrumentation. We're going to replace one of the existing mirrors in the telescope with a new one that can change its shape to correct for the atmospheric turbulence. It's tough technology because it's a very curved mirror, and things that are really curved are harder to build. But if we get it working, we'll go from the bottom here, which is sort of how much light gets through the slit and how much is wasted. And with a more compact spot with adaptive optics, it'll essentially be like making our telescope 3 times bigger or 3 times more efficient, so that we'll be able to make more discoveries, discover more planets around other stars or whatever else the telescope might be looking at. So this is exciting technology. It's still evolving as technology improves, and we're finding new ways to use it. So with that, I want to say thank you, and I'll take any questions.
Here, we can start over here.
Wait, so you said you study quasars, right?
Yes.
Don't they have like a really strong magnetic field, like spin really fast?
So there are lots of things that happen around the black hole at the center of a quasar. And one of the things is very strong magnetic fields. Of course, you also have the weirdness of a supermassive black hole, millions to billions of times the mass of our sun. And that gravitational strength actually, as something gets too close to the black hole, gets stretched out, what we call spaghettified. And that process generates a lot of heat, generates a lot of light, generates all sorts of ionized particles that create magnetic fields as they move. It is incredibly dynamic. And one of the things we don't understand as well as we wish, and one of the things we're studying, is how that all interacts.
So how do black holes get their mass? And if something living went into it, what would happen?
So let me start with if something living goes into a black hole first, because it would not be living for long once it gets too close. As I said, there's this process where things get stretched out. So you can sort of imagine, here at gravity is stronger at your feet than your head here on Earth. Now here, Earth isn't so hugely massive, you don't feel the difference. When you get close to a black hole, your feet would be stretched away from your head much, much faster, and you would be stretched, and that would be a very painful, ugly death. I hope none of you experience it, before you would end up going into the black hole. What was the first half of the question again? How do black holes get their mass? Well, they accrete stuff. So you might start with a black hole, and as stuff falls into it, disappears into the black hole, it gains that mass. And so they just get more massive over time as they suck in more stuff. What we don't know, and one of the projects I'm working on, is trying to figure out how these huge supermassive black holes formed early in the universe. Because we're finding that these supermassive black holes exist pretty soon after the universe starts forming galaxies and things. So we don't know if they all started as little black holes from like stellar deaths. Certain stars, if they're massive enough, when they die, create a black hole. They're small, maybe a few times the mass of our sun. We don't know whether those all just merge together to create bigger black holes, or if there are what are called primordial black holes that are huge bigger black holes, intermediate size, like 1,000 times the mass of our sun, that just formed as part of soon after the Big Bang, or as part of the Big Bang process. And if those later merge. So that's something we don't know and that we're really trying to study and figure out.
Okay, back over on this side.
Yeah.
If you could go to any planet, which one would it be?
If I could go to any planet, which one would it be? Oh, gosh. That's tough because every planet is so different and fascinating. But I think actually the place I want to go most in our solar system is not one of the planets, but one of the moons. There are two really interesting moons to me. There's Io, one of the moons of Jupiter, that is the most volcanically active moon in our body in our solar system. And then there's also Enceladus, which might have a liquid ocean under it. So there might be microbial life there, and it would be super exciting to go there and discover that.
What can you say about the future about like ground-based observation with the increasing amount of satellites in the sky as well as radio and light pollution with modern day?
Oh, yeah. So light pollution from satellites, whether they're emitting radio waves interfering with our radio telescopes, or the light reflected from the sun from by the solar panels, contaminating our data, it's a big problem. Astronomers are very concerned about this. We can mitigate some of it with software if we know where satellites are going to be and try not to observe when there might be a bright satellite in the way, but there are more and more satellites, that's not so feasible. Some satellite companies are trying to work on making their satellites less emissive, less reflective, but it's a big concern for astronomers, and so there's no answer to it yet, but we're trying to work in a way that will allow the necessary satellites to be there as well as not be detrimental to our science. Not sure that answers your question, but it is a legitimate concern. Okay.
You mentioned sunspots earlier and how they affect Neptune's atmosphere.
Yeah.
I was wondering what they are exactly and how do they affect Earth's atmosphere?
So sunspots on the sun are areas where the magnetic field on the sun is super strong, and it actually makes the sun slightly less bright in those small areas. But because there's very strong magnetic fields, there can be what are called magnetic reconnection events and things like that spew stuff, what we call coronal mass ejections, all these high energy particles into space. Now those high energy particles, if they happen to hit the Earth's atmosphere, can create beautiful phenomena like the aurora borealis. So that's how the aurora borealis. So we see more aurora borealis when the sun is more active, has more sunspots. And similar things probably happen with the other planets. And we know we've seen aurora on planets like Jupiter, also see aurora borealis. If the solar flare is strong enough and hits the Earth's atmosphere, it can disrupt power grids, cause power outages. It can be really very detrimental to our modern society. Fortunately, that doesn't happen very often.
Yeah. What are some similarities and differences between the storms on Uranus and the big red storm on Jupiter?
I'm sorry. Can you repeat that? I didn't catch it.
What are some similarities and differences between the storms on Uranus and the big red storm on Jupiter?
So, in principle, the storms on Jupiter and the storms on the ice giants, Uranus and Neptune, they're all gas giant planets. So a lot of the dynamics we think are very similar. The fact that the Great Red Spot on Jupiter has persisted for hundreds of years is pretty amazing. None of the storms we see on other planets have persisted so long. So there's something special about the conditions on Jupiter to allow a storm to last so amazingly long. But we don't know what the different dynamics are yet.
Excuse me?
Is that possible that a black hole will eat our solar system? And is it possible that right now we're in this black hole?
So we're probably not inside a black hole because everything's pretty stable. And we'd see some very distinct visual effects, I think, if we were inside a black hole. There are no black holes close enough to the solar system to cause us anything. I mean, a black hole is just a mass. So, for example, if for some weird reason our sun turned into a black hole tomorrow, we would still orbit it. That wouldn't change our orbit at all because the mass would be the same. So we'd have to have some big black hole come really close to the solar system to disrupt things, and we don't know of anything like that. So we're pretty safe, which is good.
I was wondering if the moon landing is real.
Well, I'm sorry?
The moon landing, is it real?
Oh, sorry, did you say the moon landing?
Yes.
Oh, yes. So the moon landing is most definitely real. Lick Observatory actually was involved with the Apollo 11 program. So Lick Observatory, even back in the 1960s, shot a huge laser at the moon. And the astronauts, Buzz Aldrin and Neil Armstrong, had put what's called a lunar retroreflector on there. And so we sent a laser from the Lick Observatory Shane telescope to the moon. It bounced off that retroreflector and came back to Lick Observatory. And they very accurately measured the timing to get the most accurate distance between the moon and the Earth. And people still do these measurements so that we can measure how fast the moon is actually moving away from the Earth.
Excellent. Wow, that's a great trivia fact to end on. So, all right, you guys, we're at the end of period 6. Let's thank our speaker one more time. Thank you for your engagement and your questions.